Hello, my name is Kevin Moy, and today I will be presenting on behalf of myself and the other authors on our paper titled An OpenAI-OpenDSS Framework for Reinforcement Learning on Distribution-Level Microgrids. In this paper, we address the issue of voltage stability in a microgrid. A microgrid is an interconnected electrical network of power sources and loads, which must be balanced at all times of operation. Imbalances can lead to voltage instabilities, which must be regulated and minimized. Below at left is a diagram of such a microgrid. A common tool for regulating the voltage is the control capacitor banks. However, this control problem is non-convex, and so analytically solving for the optimal control is difficult. Therefore, this paper employs reinforcement learning, or RL, as the basis for optimal capacitor control. Below at right is a diagram showing the overall framework of RL, where an agent reads states and rewards from an environment in one time step, and then determines an action for that time step. This action then affects the environment, resulting in a new state and reward. In this problem, the agent is a microgrid controller. The actions are enabling and disabling capacitor banks, and the states and rewards relate to the voltage measured at different nodes throughout the microgrid. Our approach ultimately led to the combination of RL with grid simulation, using OpenAI and OpenDSS respectively. The diagram at right shows the framework developed and presented in our paper. The IEEE 13 bus distribution network was used as the microgrid model in OpenDSS. Separately, a deep queue network, or DQN, was employed in OpenAI, and an OpenAI-GYM environment was used to handle state observations, rewards, and actions. OpenDSS and OpenAI are able to interact with each other via a Python OpenDSS COM interface. The blue arrows denote the flow of state information from a 13-bus model in OpenDSS to the DQN in OpenAI. On the other hand, the orange arrows denote the flow of action information from the DQN to the 13-bus model in OpenDSS. In this way, the DQN can develop an optimal control policy for capacitor bank control in the 13-bus microgrid. The DQN is trained with a series of 20,000 different load configurations for the microgrid, representing different variations in voltage that must be regulated. We compare the trained DQN with two other control methods. First, a neural network was trained using the known optimal control as an output with the states as an input. Second, the OpenDSS default capacitor control is a simple rule-based control, which enables capacitors based on local voltage measurements. These three methods were compared on a separate test set of voltage configurations for the microgrid. Our results show that the RL control outperforms both a supervised learning trained neural network as well as the OpenDSS default capacitor control. The plot below at left shows the different control strategies compared to the known optimal capacitor bank control, showing that the RL agent control policy more closely approaches the known optimal control than either the supervised learning neural net or the OpenDSS capacitor control. In conclusion, this approach allows for detailed grid simulation and system control coupled with a standardized environment for reinforcement learning. Additionally, all software is open source. Future work includes adding in control of distributed generation, such as solar PV, wind turbines, and energy storage, which will lead to continuous control. Management of islanding, i.e. isolation of the microgrid from the larger grid, leading to control of the disconnect switch, and sensitivity analysis on the available state information, leading to an analysis of the effectiveness of RL-based control with imperfect or incomplete information. Thank you.